In this lecture, we will discuss about the QSAR analysis, that is quantitative structure activity relationship. In the last class, we discussed about versatile screening on various aspects to screen specific potential compounds from a pool of compounds, right. What did we do?
So, we will take we have a library of molecules.
Right, we have library of molecules, right, to identify the potential lead compounds, right. We need to say fit between the ligand as well as the target. So, we discussed about the different types of docking, and then the virtual screening. So, first we need to prepare the protein, right, on the different aspects as well as the homology modeling if the structure is not available, and we simulated some structures for the various conformations. And for the ligand, we also analyzed the different types of ligands and made the charges and other optimization we did, and then we calculate the properties, and then from the properties of the ligands within the known activities, right, we compare the properties, right, and then finally we filter the compounds. Then we did the docking virtual screening of the compounds with the selected compounds along with actives and decoys to see whether our model could correctly identify the actives and reject the decoys. Right, then we from the docking score and the energy, right, we had to identify the potential lead compounds. Then we also discussed about the pharmacophore modeling, that is based on the conformation of the particular protein where the ligands could probably bind, then we can identify the compounds. Then the subject to experimental verifications. So, we say that some of the compounds, right, they showed the good activation, right, for example, the inhibition of more than 60%. So, now we discussed about the docking screening. So, this another approach to identify the potential lead compound is a quantitative structure activity relationship. It is a kind of ligand based approach. So, here if you have a different ligands for a particular target, and if we know the activity, then we use this information to identify some properties of these ligands to see which can relate the binding affinity or these IC50 values. So, first you get the data from the experiments. Okay, here this is the data from the experiment. So, we use this information, right, this binding affinity or this inhibitory constant, and see whether these experimental data, right, are related with any of the properties of the particular compounds. If this could be related with any compounds, right, so then we develop some models using computationally. So, here this is the computational model. So, fit the data, then we try to use the model, right, to identify new compounds, and the new compounds again this go back to the experiments for verification. So, the main principle or main aspect for the QSAR analysis is whether we can explain the biological activity of the compounds in terms of other properties of the ligands, physical, chemical or any electronic properties and so on. So, this QSAR approach, right, it tries to identify and quantify the physical chemical properties of a drug, right, and whether these properties, right, can affect the drug's biological activity using any set of equations, whether linear equations or nonlinear equations, where you can relate these properties with the biological activity. So, to identify the consistency of this activity and the properties, we can set a kind of rules and evaluate the activity of these new compounds. With the new known compounds, if you make some rules, then we can adopt these rules to identify the new compounds. This is essentially you can see the biological activity, that it is a function of the molecular or the fragmental properties. If you have the ligand, either the molecular properties of the individual fragments and sum of everything, or the whole or say whole, you can see that this is a function of the different properties of the ligands can explain the biological activity. This is the principle mainly used in the QSAR studies, right. So, why do you need the QSAR analysis, right? As we know, if you want to do any experiments, it is time consuming, it involves lot of manpower, and also it is very expensive, because every chemicals we need to trial and method, and it is very expensive. Then also it also required the animal test, right. So, if you could identify the potential compounds from the 2.2 million compounds and you identify 10,000 compounds, then you can reduce the number of experiments, right. In this case you can increase its efficiency, right, of identifying these compounds, right, and also you can promote this green chemistry, right, avoiding the experiments. Then again if you see the in vitro and vivo potencies of drug, it varies with different factors. For example, the intrinsic reactivity and the solubility of in water, because it is to be soluble, right, and the ability to pass the blood barrier, brain barrier and so on, right. So, differential behavior of these aspects, it also attributed with the electronic and steric properties of the structure. For example, the reactivity of the drug or the solubility or this ability to pass the blood brain barrier and lot of other properties that depends on the electronic and steric properties. In this case, if you relate these properties with the function, right, in this case you can better develop a model, and that model will be helpful to narrow down the available ligand molecules. So, this is the workflow for the QSAR. So, first what are the requirements of QSAR analysis? For the case of docking, what are the requirements? We need the protein and we need the ligand, then we will dock that. But here first we need the collection of ligands, we can with known experimental data. For example, you use the ChemBL, right, or the Timbal databases. This will provide the experimental affinity data or the inhibition constant for several ligands, right, with respect to different targets. So, you can use any specific target, you can get all the ligands for targeting a specific protein. This is on one side. On the other side, we need to have the descriptors, right. There are various descriptors we can define, for example, molecular weight or the hydrogen donor or etc., right, several features you can select. So, either you can use the known compounds and develop the features, or there is one program called the Paddle descriptor. This will provide, if you give the compound, this will provide a set of features, about 700 to 800 features it will give. Then these many features are repetitive. In this case, you have to use feature selection method, either objective feature selection or the subjective feature selection. Subjective ones, we can see there are several properties which are closely related to each other. In this case, you can use correlation coefficient approach to discard the properties if they are having a high correlation, for example, say 0.9 or more than that, right. Likewise, we can do the objective feature selection, and if sometimes we know some properties are important, right. In this case, we need to keep these properties for fitting the model, that is called the subjective feature selection. So, you can do both ways for selecting the important features to develop a model, and once we select the features, then we construct a model. There are various ways to construct a model, either the multiple regression analysis or you can develop any nonlinear models, right, to relate the experimental IC50 values, right, you can get from the databases plus these properties, right. Then we need to validate the model, right, using the jackknife test, or you can use any blind test set to see whether this can predict reliably the activity of any new compound, right. So, I will discuss about some of the databases, right. As I mentioned earlier, there are several databases which contain the record of the ligands, and some of them with the affinity data or the inhibitor constant data. For example, the ChMBL, it has more than 10,000 targets, right, and the target records more than 1 million target records, right. Also they have the 13 million, right, the activities. They did the detailed literature search because they include about 60,000 publications, right, in the database. So, this is a website for this database ChMBL, right, you can utilize this database and you have various options to get the data. For example, you can search with the ligand, search with the target, right, and also you can search with the drugs, approved drugs, that also you can search. So, you can search the data or you can contribute the data, or also you can give the feedbacks, and also they give all the different information, right, from this particular database. They are also focusing on some specific diseases, for example, the malaria drugs, right. So, specifically the drugs they used for this malaria. So, you can use this information to get these ligands and which drugs and which compounds are used for different diseases, or they are identified as the drug lead molecules, or you can give the activity with respect to a target. So, you can get a set of data from Kimball database. This another one is called the Kimball database. Here also you can get the different ligands based on any target. For example, it is a tubulin I use, right, so tubulin search, right. So, these are the various ligands, okay, these are the various ligands, right, which are related with this tubulin. So, they interact with the tubulin. So, you can know the binding mode and the binding site as well as the activity data for all these small molecules. Likewise, there is various other database available, right. Sometimes they have these experimental data, sometimes they have the information regarding the small molecules. Even the protein data bank, you can see several complex structures, right, of the proteins with ligands. So, there you can get the mode of binding for all the ligands with respect to any specific protein. So, that is you can understand, right, how the ligands interact with a particular protein. Some of the examples, you can see zinc database, it is about 35 million compounds, now it is growing, right. Cinnamon 2.2 million compounds, and there is database for the Chinese medicinal compounds about 45,000 structures, and Kimball is 1.7 million, and specifically on the malaria they have data for 371,000 ligands, right. So, you can utilize the information available in different databases, right, to collect the data of the ligands on various aspects, either the ligand structures, or you can get different properties of the ligands, or the experimental data on the binding affinity or the inhibitory constant, or you can see the binding mode, right, how the ligand interacts with a particular protein, right. So, using this information, if you have the ligand, you can derive various properties, right. Some of the important properties which we discussed, right. Last class we discussed about Lipinski's rule of 5. What is Lipinski's rule of 5? Molecular weight less than 500, hydrogen donor less than 5, hydrogen acceptor less than 10, and log P less than 5, right, the partition coefficient is less than 5. So, like this you can derive various properties, right, for example, molecular weight, hydrogen bond donors or acceptors, number of rotatable bonds, right, and the hydrophobicity. These are the important features which can relate the ligands with the protein, because in the case of the target protein you can see different amino acid residues, they are having different characteristics. So, they like to perform different types of interactions, right. For example, they can make the hydrogen bonds if the donor is in the protein side, right, then in the ligand side if you acceptor, then they will have high tendency to interact. Like number of rotatable bonds, this can make various conformation, based on the conformation, right, the ligand how they can interact. Then the cavity, depending on the cavity size, the ligand can bind or not. This is the reason why we consider about the molecular weight, right, depending upon the cavity. So, then hydrophobicity, if there are hydrophobic groups, right, in the protein side, then it requires the hydrophobic side chains, right, in the ligand side to have these interactions. So, likewise you can derive various properties, and you can make the selection based on subjective selection as well as the objective selection, right, based on the computationally you can calculate the similarities and you can select, or you can use the important properties subjectively. Then how to get the experimental data, right, they have various experimental techniques used to get the IC50s. One is a functional antagonist assay. So, you can get the IC50 values, right, for any antagonist, by determining the some concentration needed to inhibit the half of the maximal biological response, right, of the agonist from the dose response curve. We can get the dose response curve, and you can see how much the concentration is required to inhibit half the maximal biological response, right, you can do it. Likewise, there is another assay, for example, competitive binding assay. Here also you can see a single concentration of this any radioligand, usually agonist, in every assay tube. Then you determine a specific binding of the radioligand in the presence of competing non-radioactive compounds, usually antagonist. Then there is a balance, right, for measuring the potency. Then you can see the competition curves, right, they can be fitted using computer models like logistic function, right. So, to see the fit. So, different ways to get the IC50 values, right. You can use the competitive binding assays or you can see the functional antagonist assays. I will show you how to get this one. So, here this is the curve, here x axis is the concentration, this is the concentration and y axis is the inhibition. Okay. So, if you see this is the 98% the maximal inhibition, right, you can see the curve. Now, this is a usual curve we will get for the inhibition with respect to different concentration, right. Then if you goes to the lowest one, the minimal inhibition is 10.629. So, then we get the 50% of maximal inhibition. Why is IC50 we mentioned? Because we need to have a balance between the inhibition and the viability. This is the reason we take this 50% inhibition. So, we calculate the 50% of the inhibition. So, this is the maximum 98.76, right, minus 50% of the difference, how much there is inhibition. The difference is 98 minus 10, this is the maximum 98, so minimum is 10, so that is the difference. So, from the maximum we get reduce 50% of this difference, this will give you 54.69, right, the inhibition. Then we go with this 54.69 percentage, so somewhere here, right. So, if you look at here, okay, this is the place where we touch the curve. So, this concentration, okay, this is the concentration, this is about this is 10, this is equal to 12.869, right. This is how we get the IC50 values. So, for this compound the IC50 value is 12.869. If you take the log values, this will be 1 point something, right. So, here if you see relate the concentration with the inhibition. So, you get the maximum concentration inhibition and the minimal inhibition at various concentrations, and using this information we can get the 50% of maximal inhibition, right. So, for the 50%, what is the concentration related to 50%, that you can see this will be the IC50 value for that particular compound. So, experimentally we know that using different assays, right. So, now we have these experimental values, experimental data. So, we need to relate with these computational models, right. So, in this case we can have various types of QSAR models based on dimensionality. You can see 1D QSAR, 2D QSAR, 3D QSAR and so on, right. In the 1D QSAR, right, so you can correlate with some of the globular properties of these molecules. For example, you can see the pKa, we get only one value, right, or the log P or different properties. So, here we will get only one value, so it is one dimensional. This is called the 1D QSAR. When you go with the 2D QSAR, we go with the one step further. In this case, you see the connectivity, right. So, you see the patterns and how the interactions are connected. So, you give the connectivity, this will give you 2D QSAR. When you consider the surrounding environment, right, for actually different types of interactions surrounding that particular position, then we can go with the 3D QSAR. Then along with that we can see the ligand configuration or the induced fit models, or you can use solvent models, solvation models. So, accordingly you can increase the complexity, right, to build up the different dimensions of this QSAR, right. Mainly you can see this 2D QSAR, 3D QSAR commonly used in the when developing the models along with this 1D QSAR. So, here you can see the how they develop the model, right. So, for example, if you see different molecular structures, right, here you can see this is the you can see the 1D, right, the first 1D QSAR model, because we can get some properties using these specific compounds, right, based on the atoms present in the particular compound. Then second we get the connectivity. So, which residue, which atom is connected to which position. So, here this will get to 2D QSAR. Then if we go to 3D structure level, so what are the neighboring current surrounding residues and how there are interactions made between these different atoms, we give that information, then we go with the 3D QSAR. So, there are various molecular descriptors, right, for example, electronic properties, hydrophobic properties, solubility parameters and the steric parameters. So, there are topological parameters, right. So, various parameters we derive from this 1D information or 2D information or 3D information, right. So, once we derive the descriptors, then we need to pre-process the data, whether the data set is fine or any discrepancy in data set, right, or we need to standardize the data, right, then they normalize the data. If it is a wide range, then we have to normalize the data. Then we need the feature selection, so and see any features or outliers and so on. So, do all these pre-processing, right, once we have the descriptors. Then we need to feed this into some type of techniques like statistical methods or in machine learning techniques, right. For example, multiple regression techniques or support vector machines, neural networks, right. So, when we feed this into any of the methods, then you can evaluate, right. We have the values for the experimental data and you have the QSAR model, right. You use any model to calculate the values, then you can evaluate whether the model could correctly predict the values of these any new compounds, right, the any IC50 or this any activity. So, you can use R, right, this is a correlation coefficient between the IC50 values, right. So, if you have the IC50 predicted versus experimental, right, then you can calculate the correlation, see how they can fit, or you can calculate the mean square error and see how far the actual values, right, or the predicted values deviate from the actual values, right. You can see from that you can see whether this model fits well or not. This is the one example, this is almost perfect fit, right. This we do not expect this type of fit always, right, but if you are lucky enough then you are able to get a good fit between the experimental as well as the predicted activities, right. Now, we will explain the details how to do this. So, if we go for the molecular descriptors, so what do you mean by molecular descriptors?
Property.
So, these are the numerical values, the property values, numerical values that characterize the properties of the molecules, right. There are various type of properties. For example, some properties you can measure, right, density you can measure if you have the compound and pKa and the refractive index, and we can see some properties of measurement properties. Some properties you can calculate, for example, surface area, van der Waals surface area, molar refractivity, all these properties you can calculate. Then there are different types of properties like chemical properties or the biological properties or the intrinsic properties. For example, the chemical properties you can see pKa, log P, solubility and so on, and the biological properties toxicity, activity and so on, and the intrinsic properties like charge distribution, polar surface area, molecular weight on this area. So, you can see intrinsic properties of any ligand, chemical properties and the biological properties, right. So, you can have the biological, chemical and intrinsic properties. Right. So, then you can get some of the calculated properties and some of them we can have the measurable properties. Then we can see these descriptors in different groups, like you can say geometric descriptors or you can topological descriptors or the electronic descriptors. For example, if you see the 3D aspects such as the moment of inertia that we discussed earlier in the calculating the moment of inertia from 3D structures, right, and also accessible surface area. Right, how to get the accessible surface area? By rolling a water molecule, so how far the each atom is accessible, right, you can get this one, you can get the information. Then also you can get some type of graphs, right, some of the this is some of the nodes where they have the different protein or the molecules interact and some edges, right. So, for example, this is the isopentane is here, this CH3, CH3 and CH2, this can graphically represented, right. So, you can see here this is a node and you can see there are some edges, right, you can graphically represent. Then also you can get some electronic properties, right, because these properties are also important, right, to define the activity. So, you can get the energy map, you can see some of them are green, they are accessible, and the red one, right, which are having the high energy system. So, you can see the different types of molecular orbital energies and dipole moments you can calculate for any compounds, right. These are you need to understand the concept to calculate. I will explain some of the parameters how to calculate, and if you have this software you can automatically give you all the properties. If you give your compound, right, in SMILE format, or you can give you the structure formula, right, automatically it will give you all the information regarding a particular ligand, right. So, now if you have this data and calculate the all the properties, right, then to obtain the reliable QSAR models, right, we need to ensure the data are of high quality. So, in this case we need to pre-process the data to ensure that the data are high quality, they are testable and there are no duplication of data, right, and all the data which resembles uniquely for any specific compounds with respect to specific target, right. So, you need to check all the data, this data cleaning is very important, right, check all the data and see whether any data are missing or the compounds are known with known structures, right, and the experimental data are obtained reliably, right, all the information you need to collect. Then we need to change the transformation, data transformation into the different properties, right, and then from these properties we need to select the features, right, for each molecule. Okay, then how to get this data cleaning? Sometimes maybe error and inconsistencies, right, such as missing data or the incomplete data or sometimes invalid character. If it is available, then you need to remove it. Then the second aspect, you need to remove the redundancy. If same information available, right, in the list of compounds, then we need to remove the redundancy, right, and eliminate the redundant ones. Already we discussed about the removal of redundancy in the case of protein sequences and the protein structures. Likewise, ligands also we discussed, right. What is the measure used to remove the redundancy in the ligands? Tanimoto coefficient, right, yesterday we discussed. So, we have different groups and for each group, right, we see whether this type of, for example, ring, the ring is available in compound 1 and compound 2, right. If it is both are available, then put 1. Likewise, we do for the different parameters and we use a Tanimoto coefficient, right, A by A plus B plus C, right. Then if it is more than 50%, right, then you can see they are redundant. Likewise, you need to remove the redundancy for any group of ligands. Then the second one, we need to do the data transformation. For example, whether the variability of data, right, there exists a great deal of variability in the range, right, and the distribution of each variable in the data set. Right, we should not remove the variable ones, we need to keep as much as possible the variable data, and whether our model could identify all these ligands with different immunity constants, right. So, that is very important. Then how to do this? You can handle by using say some kind of normalization or the standardization. Sometimes you see the variables very high value deviation, then you can use the normalization or some data standardization procedures, so that you can see a specific range, right, and then you can handle the data. For example, in the QSAR studies, most of the inhibitory constants, right, they range from millimolar or micromolar or nanomolar. In this case, we get a wide range. So, take this logarithmic of the scale, right. In this case, you can be standardize the values in a specific range and you can accommodate almost all the ligands, right, in your data set. Okay, then the next step is a feature selection. This is very important because what are the features you select in your model, that will give you the reliability of your model, because if you choose wrong features, right, then you can reproduce the data, but when you go with the real test set or the new data, in this case your method will fail. So, you have to be careful about the feature selection, that should be at least explain the activity of your particular compound. So, we choose the features, right, take some of the features, this is why we need the subjective selection, right. If you need the hydrogen donor or hydrogen acceptor or the hydrophobicity, right, or molecular weight, these features are important to explain the property of any ligand. So, we need to be very careful to the feature selection, right, what are the relevant features, right, for the constructing model. For example, if we have a data set kind of 150,500 variables, right, only if 15 of those may be meaningful relevant, right. So, we need to take only the relevant information. So, here we have the original feature set here, right. Then first we need the subset, from these original features we can get the subsets, and from any candidate subset we evaluate the features, right, and if this explains well the your activity data, then it is go with the selected subset. If not, go back and get generate another subset, and from the subset you select the candidates and then again evaluate whether this can be able to explain the activity, and then if yes, then go with the selected ones, or repeat again unless you are satisfied with the feature selections as well as the relationship with the experimental data, right. So, now you can select the features, right, then we need to build a model.